Okay, 6.3 was about how to use alternating current in our houses. It's about that. In section 1, we studied the principles of electromagnetic induction. In section 2, we studied about the devices which produces AC, which is the AC generators, and DC generators. Section 3, now we produce AC. How can we use this AC in our houses? This section talks about that. First, we know that a generator produces an alternating current and at the same time alternating EMF. They happen at the same time, and their equations are also the same. This is the EMF equation. In 6.2 we write it. Instantaneous EMF is maximum EMF multiplied by sine omega t. In here is the omega t was theta, also represented by angle theta. And at the same time, output of a generator as an electric current is the same function. Instantaneous electric current, which means dependent on time, as time is changing, is a sine function. Sinusoidal variation of current in EMF is equal to maximum electric current multiplied by sine omega t. Only difference is in this section, we are not going to use E, we'll use V, potential difference of the generator. So V is equal to V max sine omega t, they are equal to each other. And how electric current and potential difference of output of generator, AC generator changes, we know it. It changes as a sine curve, sinusoidal variation. So it's a sine function. Both electric currents and potential difference of output of the generator. And they are changing between two maximum values. Electric current is changing between positive maximum and negative maximum. Potential difference is also changing between positive maximum and negative maximum potential difference. And we'll learn in section 2 what is it equal to. BAM omega yani bağını, bir şey like this. Okay. And when we define AC, when we will define AC, of course we are going to first talk about AC in the 11th grade. What is AC? Difference between AC and DC, what is it? In AC, in DC we have a battery, positive and negative terminal. So positive terminal, negative terminal. In electric current is from positive to negative, it circulates in one direction like this. But in AC, it's not like this. Generators have no fixed positive and negative. One side is once positive, other side is negative. Then it changes. Remember the shape, look at that. Positive, one side, then it becomes negative. Then positive, then becomes negative. Yeah, continuous, the polarization is changing. So positive, negative, then negative, positive changes like this. Which makes electric current junction to be continuously changing. Once clockwise, then counterclockwise. This happens in 1 second, 50 times, which is called as 58 cycles of variation of direction. Remember, we define the frequency of AC. So, but both of them have can be calculated by the same equation. Yeah, the Ohm's law can be used for both DC, direct current, and for AC. You can use it. So, for example, if I want to use the electric current in this circuit, what I have to do? I have to use Ohm's law. What is it? Divide by potential difference, how much? 15. How much is the resistance? 3. I will divide them, I will find it. But in here also I will do it. The only one difference, because AC is continuously changing, maximum value generally given to us, not this VM. VM is how much? 15. How can I calculate maximum value of the electric current I am? Again, also. So I will divide 15 by 3, it's going to be maximum value. Yani VM divided by how much is VM? 15. How much is R? 3. Result is 500. And also, but in DC, it's all the time 5. Yeah, I'm going to use again the same equation. I is equal to, how much is it? V divided by R. How much is V? It is 15. How much is R? 3. So result, again 5. Just differences. This is all the time 5 ampere, but electric current of the resistor in here is not always 5. Maximum value is 5. It's changing between positive 5 and negative 5, like that. So that's why if I draw graph for AC and DC, it's going to be like this. If I show that to you. For example, this one is DC. Potential difference is 15 volt. And what is electric current? How much we calculated? 500. All the time. 15 and 5. But in AC, it's not like this. It's changing between positive 15 and negative 15 in potential difference, electric current positive 5 and negative 5. This is sinusoidal variation of potential difference across the resistor, and also electric current on the resistor. One positive, one negative, and so on, changes like that. So electric current and potential difference in the AC circuit continuously changing, but in a DC, they're all constant. Same direction, same magnitude. And for both AC and DC, we can calculate the power. Both AC and DC, we can calculate the power. First, I'm going to find the DC power, which is studied in the 11th grade. Power of a resistor. When some electric current passes on a resistor, it produces power. Power is, in fact, in the resistor, it appears as a heat. All heaters now we are using at home the same. When electric current passes through a resistor, it can start giving out heat. Power means that, in fact. Okay. Power of a resistor is calculated in a DC circuit by the product of electric current, yani we'll multiply electric current, and potential difference across the resistor. Yani how much potential difference across the resistor in here? It's V. How much electric current on the resistor? I. When I multiply this V and I, we will find how much is electric current on the direct current. This equation is direct current equation for power. And we have two alternative versions of these equations. We can insert Ohm's law for V, which is I times R, it becomes I squared times R. Or we can insert for I V over R, which is going to be V squared over R. So these three equations are equations for calculating power in direct current, which is the current all the time, unchanged. Same direction, same magnitude. Depending on what given in the question, you can use one of them. For example, if the question gives you V and I, so I'm going to choose this one. If question gives you V and R, we are going to choose that one. If the question gives you I and R, generally which we are going to choose in this section, we are going to choose this one. All these are DC power equations. But AC power and DC power are slightly different. What is the difference? Because even though both have this maximum, same maximum value, like this, forget that, maximum value of AC is 5 and negative 5, the change between negative and positive, but DC all the time 5, their powers are not the same. In fact, it makes sense. Because DC, all the time, 5, but AC, 5 in here, 5 in here, 5 in here, 5 in here, but between them, less than 5. Even sometimes, 0. So it's like AC power always less than DC power if we make their currents same. So, an equal maximum current is energy produced by an AC circuit, and DC are not equal. Which one is less? Of course, AC power is less. How much less? Half. It's important. Yeah, power dissipated in AC circuit of maximum current. Yeah, this circuit's power and that circuit's power are not same. It is half of this one. Why half? Because as I said, AC is maximum at some instance, but DC is maximum all the time. Reason is that. Then we are going to write now. We write already DC equations, power equations. What were they? Power is equal to I times V, I squared times R, or V squared over R. These are all DC power. Now I am going to write AC power by using this expression. Like this. If power displayed in AC circuit is half of the power displayed in a DC circuit, so I know what DC circuit equations. It is equal to IM squared times R. So it's going to be, in this case, corresponding equation is going to be what? IM squared R divided by it's half. It's half. If this is the power calculated by AC circuit, this is the power calculated by DC circuit. Then same equation is going to be divided by 2 in AC circuit. This is the power equation of the power calculated in the DC circuit. This is the equation of the power calculated in the AC circuit. Not only for these two, we can also do it other equation I will do next slide. But if power distributed in AC circuit is half of power of DC, you can think opposite. DC must be twice. DC power is going to be twice. Then power distributed in a DC circuit of a maximum current IM twice is the power distributed in the AC circuit of steady current IM. And they're going to be opposite. This is going to be maximum. So this is maximum and this is steady. DC is steady, but AC is maximum at some instance. Then I'm going to show all of them. This is power in DC circuit. So the power dissipated in AC DC circuit of steady power is equal to I times V. So the corresponding in power equation power is going to be IM times VM divided by 2 because half power of AC is half of DC. I can write power equation in DC circuit in terms of electrical and resistor I squared times R. So AC is going to be what? IM squared R divided by 2. If I write power in a DC circuit by VM squared times R divided by R, corresponding equation in AC is going to be VM squared R divided by 2, yani VM squared divided by 2R. Yeah, if maximum value of the AC is given to you, maximum value of AC is given to you, as I said, instantaneous value of the AC is continuously changing, that's why always they will give you what? The maximum value if they give. So if maximum value of the electrical and potential difference are given, this is the equation. How we calculate the power of this AC. If maximum electrical and resistance is given, this is the equation. How we calculate AC. If maximum potential difference and resistance is given, so you are going to use the equation for calculating AC power. But in DC, I and V all the time same, that's why we don't need to divide it into two. IV, I squared R, V squared over R is the equation for the AC. Okay. Then, if the maximum current of AC circuit is greater than the steady electrical DC circuit, AC circuit can have equivalent heating gap to the DC circuit. Normally, when they have equal electric currents, we know that they can never have equal power. When DC current and AC's maximum current are equal, they can never have equal maximum current. What should I do? I have to increase maximum value of AC to make them equal in power. We will do that. Or I have to make value of DC less than AC. But how much less or how much more? Now we are going to answer this question. If I want to make the powers equal, how much more I have to do IM of AC or how much less I have to do I for DC. Now we are going to answer this question. Okay. Alright, I did it. As you see, maximum value AC is some more than DC, or current of DC is some less than maximum value of this AC. Now they are equal in power. Assume that they are equal in power. Now I am going to write their equations. What is power equation for the AC? I know it. No divided by 2. I DC squared times I. But power of an AC is not like this. I am using IM value, but IM is maximum at some instance. That's why I had to divide IM squared by, which was the half. Then mathematically, I make them equal in power. I make them equal in power, but how? What is the relation between these two values? Now I will get it. Okay, so let's make equal then. If this DC power and AC power are equal, if I write them, make them equal, these R's will simplify. DC current square is equal to maximum current square of AC divided by 2, but it's about square part. So if I want to get a relation between direct IM and IDC, I have to take the root. When roots are taken, so I will see this. DC current must be less. Yes, DC is less than IM. But how much less? Divided by 2. If I want to calculate IM, what should I do? Cross product. Yani IM is equal to root 2 times IDC. In this case, if this relation exists between this IM and this IDC, then I will say that they are equal in power. They are equal in heating effects. So this is a fact. But I explained this for just one definition to ego group, which is known as effective value. So what is effective value? Now let's talk about this. Now I know that this DC and this AC are equal in power. Let me show like this to you. This DC, let me write this. This IDC and this IM, they have this DC circuit and this AC circuit have equivalent having effective equal power. In the case, how? If this IDC is equal to IM divided by root of 2, or if this IM is equal to what? IDC times root of 2. Now they have equal power. Then now, because they have equal power, equal heating effect, this DC current is given a name, which is named as effective electric current of who? AC. Effective electric current, yeah, like equivalent like this one. This DC value is known as effective electric current of this AC. Then we are going to calculate effective value. What I have to do, I have to divide maximum value of AC by root of 2 to calculate effective electric current of that AC. Then definition is going to be this way. If I define it, this is the definition in the book, how effective value is calculated. Now we will go on this basic what we studied. First, AC and DC, they have equal powers, then we can define effective value. Now come on. As you see, there are two currents in this graph. One of them is, red one is alternating current. The black one is direct current, which is DC. Then now definition, we get the definition. These two currents have equal power. Yeah, this IM, alternating current represented by IM, and this direct current represented by IE have same power, same energy, same heating effect. Then definition of the effective current. The amount of direct current, yani this IE. Amount of direct current, this IE. That would dissipate equal amount of energy in resistor. Two alternating current, yes, they have equal power. They will dissipate equal amount of electrical energy. Yani this DC and this AC will dissipate equal amount of electrical energy. The amount of direct current, i.e., that would dissipate equal amount of energy in a resistor to an alternating current of maximum value, how much? IM over a cycle is called as effective value, or another name, root mean square value of the DC. And how we calculate I effective? I will divide maximum value by root of 2 or cross product. How can I calculate IM? IM is equal to I effective times square root of 2. Then these two DC and this this AC will have equal power, equal heating effect, equal energy. As you see, because IM is divided by root of 2, this IE is going to be always slightly less than IM. Yani IE is, also in the graph you can see that. IE is less than IM. IE is less than IM. Alright, this is what effective value is. But effective value is not calculated only for current. Because we know output of an AC generator also changing as output potential difference of the AC generator also changes the sign function like this. This is potential difference of the generator. Look at that. It's changing as an AC sinusoidal, just like current. So we can also calculate effective value for potential difference by the same way. So if I divide maximum value of the potential difference of AC by root of 2, we will calculate what? Effective value of this potential difference, maximum potential difference. Then cross product, also we can calculate Vm by V effective multiplied by root of 2. And one more thing, every measuring device measures effective value. Why? Because instantaneous value is continuously changing. In 1 second, 50 times frequency. Maximum value is maximum only at that instant. So if I take this maximum value, it's going to be not correct because it's not all the time maximum. Then what should we do? I will take what? This effective value. Why? Because this effective value is power and AC's power are the same. That's why these measuring instruments, it can be voltmeter or a meter or any instrument which measures the potential difference of electric current, they always measure effective values, not instantaneous value, not maximum value, only effective value. This is what it is. Now, after that, we define effective value, what it is. We are going to now define pure resistance circuit. Then we are going to connect a resistor to this AC circuit. First, what is a resistor? We know that if a conductor has some length, we conduct some length, this is cross-sectional areas, S or A, and then a kind of some type of conductor which can be silver, copper, aluminum. So every conductor will have some resistance. So it's called a pure resistor. And why is it pure resistor? In fact, straight why is it pure resistor? Why is it pure resistor? Because it's not a coil. It doesn't make a loop. Because when you make a wire a loop, it becomes a coil. Every coil has some coefficient of self-induction. And when you say that pure resistor, it's not a coil, it must be a straight wire. A pure resistor is a resistor with no self-induction. Yani, it's going to be a straight wire, not a loop. And in the 11th grade, it studied that resistance of a conductor depends on 3 things: its length, cross-section area, thickness, and type. This, when you cut a wire whose length is specific, whose certain cross-section area, a certain type, so its resistance is going to be a certain number. Only one thing in the 11th grade you studied changes the resistance of this wire. It is the temperature, nothing else. That's why when we connect a resistor to an AC generator, according to Ohm's law, because that is constant, V and I, on this resistor changes directly proportional. Because this is unchanged. And if the potential difference of the generator is changing on the resistor, so electric current is also changing proportionally. Yani, according to Ohm's law, electrical and potential difference across a resistor is directly proportional, which means reading of this voltmeter, which measures the potential difference on the resistor, and electric current on the resistor are parallel and directly proportional changing. Yani, reading of the ammeter and voltmeter increases together, decreases together, becomes zero together, maximum together, which we named as being in phase. They're in phase. Also, we studied in chapter 7, remember. If 2 waves are changing together, these 2 waves are in phase in constructing interference. Remember, waves are propagating in the same direction, they were in phase. This is how potential difference electric current is changing across a resistor, on this resistor. As you see, they are zero together, maximum together, decreasing together, zero together, decreasing together, so they are in phase. Because they are in phase, they will have the same function. This is potential difference function across resistor. This is the electric current of the resistor. Both have the same function. I am sine omega t, we am sine omega t. Sine omega t, sine omega t. This is instantaneous electric current. How this blue is changing, which is the electric current. This is instantaneous potential difference. How this red current is changing. So they are in phase. If they are in phase, we can represent these 2 vectors which are in phase by 2 vectors which are in the same direction. This is called phasor. Because angle between them is 0. And also, there is no phase angle difference between potential difference electric current and resistor. omega t, omega t. Omega t is the phase of potential difference. Omega t is phase of electric current. So difference between the phase is zero. That's why we say that in a resistor, electric current and potential difference are in phase. So the phase angle between them is zero. That's why we represent IR and VR as two vectors in the same direction, which there is no physical difference. And we can calculate R again by the same value, V effective divided by I effective, or V maximum divided by I maximum. It's okay, what can be used? Teacher, how they can be equal? Because very easy. VM, how do you calculate VM? V effective times root of 2. How do you calculate IM? I effective times root of 2. So this root of 2 will simplify, you'll get that. Yani effective value divided by effective potential difference divided by effective value of the electric current, or maximum potential difference divided by maximum value of the potential difference. For a true resistor, we will calculate resistance of that resistor R. And one more thing. Change in frequency of AC generator does not make a change in resistance of the true resistor. Yani resistance of the true resistor is not affected by frequency of the AC generator. Because resistance equation depends on length, cross-section area, and type of the conductor. So nothing, only temperature, only these four quantities. Nothing else can make a change. In resistor, we can increase the frequency or decrease the frequency, doesn't matter. Even resistance in DC and AC is same. And in direct current, how much resistance you calculate for a resistor, in AC you will calculate the same value for the resistor too. But coil is a bit different. Pure coil, pure inductor. A pure inductor is a coil itself, induction with negligible resistance. This time we are going to do opposite. It's going to be a loop, low loops, which is called, we name as inductor. But this time resistance will be considered to be zero. L is not zero this time. But in the previous one, L was zero, but R was not zero. In reality, no conductor has zero resistance, only superconductors. But we are going to think ideal cases. We will consider that this coil has almost zero resistance. It's a pure coil, pure inductor. So a pure inductor is connected to AC generator. And this ammeter measures electric current, this voltmeter measures the potential difference across the coil. So how V and IL changes now on the resistor, on this coil, we are going to think about this. One thing we know at the end of the 6-1. As electric current on a coil is changing, coil was reacting to this change, which is according to Lenz's law. It was induced electric current in the opposite direction, if you remember. So there was a DC, when we switched on, electric current was jumping from 0 to maximum value, magnetic field of the coil was jumping from 0 to maximum value, magnetic flux through the coil was jumping from 0 to maximum value. Coil was reacting this jump and producing an opposite directed current, we named as self-induced current. And instantaneously, net current becomes zero, even though you give electric current, self-induced current makes it zero. For that, in coil, because of the self-induced current, at the beginning, when generator provides maximum electric current to the circuit, zero to maximum, because of self-induced current, that current becomes zero. They're opposite directions. That current becomes zero. And at the beginning, ammeter reading is zero because of the self-induced current. Voltmeters, maximum. Why? Because maximum current provided by the generator and potential difference is also maximum. Yeah, potential difference is maximum, electric current is zero. Voltmeter is maximum, ammeter is zero, which means they are changing oppositely. Then voltmeter reading becomes zero, ammeter becomes maximum. Voltmeter decreases, ammeter reading increases. So they are changing oppositely, inversely proportional. This fact, and reading of the voltmeter and ammeter are changing oppositely in a coil is known as being out of phase. So in a pure inductor, then electric current IL and potential difference VL are out of phase. But how out of phase? What does it mean? They are not increasing together. These waves are changing oppositely. Yes, that's the difference. Because when potential difference is maximum, after some angle, electric current becomes maximum. How much is this angle? This angle is pi over 2. When electric current potential difference becomes 0, after some angle, electric current becomes 0. How much is it? Again, pi over 2. Yeah, the phase angle difference between potential difference and electric current is pi over 2 in a pure coil. So then we say that in a pure inductive electric current, I have potential difference will out of phase by an angle of pi over 2. Which one is leading? Potential difference is leading. Why? Because self-induced current makes electric current 0. So that's why potential difference across the inductor leads the electric current by pi over 2. That's what we are going to try. When potential instantaneous potential difference equation pi over 2. So it is sine omega t plus pi over 2 if electric current is I am sine omega t. And phase of the potential difference is omega t plus pi over 2, but phase of the electric current is just omega t. Then I am going to now represent this phase again by phasor, which are two vectors, but this time vectors are not going to be in the same direction. If they are in the same direction, and phase angle difference between them is 0. Now, what is phase angle difference between them? Pi over 2. So I have to draw I R and VR perpendicular to each other like this. Look at that. This is IL, electric current on the coil. And potential difference is leading the electric current by pi over 2, so that's why I have to draw potential difference by rotating pi over 2 clockwise because of this positive, counterclockwise because of this positive. This is phasor for pure coil. How potential difference and electric current are related in a coil. And again, VE over IE or VM over IM defines a property of the coil we named as opposition of this coil to electric current. Yes, coil also opposes electric current. But what is the nature for this? Self-induction. Self-induction makes electric current and opposes the electric current of the circuit or of the generator. So then, if I calculate this opposition of the coil, if I give a name to opposition of this coil to the electric current, this name is called as inductive impedance. It's the same because volt divided by meter, volt divided by ampere, volt divided by ampere, always equal to the same as the resistance. Resistance was also like this, but only their natures are different. In resistance, remember I told you about this. In resistance, mobile electrons are collided with immobile electrons, and then that is the opposition of the resistor to electric current. But in here, no collision, no resistance. What is the opposition? Because of the self-induction of the coil. The natures are different, but by Ohm's law we can calculate all the oppositions. Opposition of the resistor, opposition of the coil, or opposition of the capacitor. Next time we are going to study. Okay. So the inductive impedance XL is the opposition of the inductor to change of electric current in the circuit. If it's about self-induction, of course there must be, in this equation, there must be two quantities. One of them is coefficient of self-induction must be in the equation. But also, one thing must also include in here, what is it? Frequency. Why frequency? Because change in electric current is represented by what? Frequency. That's what the equation of the XL must include. Frequency, yes, look at that. XL is equal to 2 pi f L, yes, frequency included, because as frequency increases, change in electric current becomes faster and faster, opposition becomes greater, and also coefficient of self-induction L must be included. Yani 2 pi FL is the equation for calculating XL. 2 pi F omega, I can rewrite this equation also in terms of omega and omega times L. One thing we have to know, frequency makes a change in inductive impedance. Remember in the previous title? Frequency has no change in resistance, true resistance. This is Miller's question. Frequency of AC cannot make a change in resistance, but it makes a change in inductive impedance, even directly proportional. If frequency of the generator increases, XL proportionally increases. Okay, then one more device we are going to study, and then today we are going to finish the first part of this 6.3. Next part we will continue next lesson. Okay, then capacitor. We are going to connect this time a capacitor to AC generator. And we connect a voltmeter on the capacitor to measure the potential difference from the capacitor, and an electric current ammeter to measure the electric current. First, know that what is a capacitor? Capacitor is a device which stores electrical energy, electrical charge. And generally, we represent a capacitor, the simplest type of capacitor, was parallel plates, conducting plates. Every conductor at the beginning is neutral. Neutral means equal number of positive and negative charges. When a capacitor is connected to a battery, this capacitor becomes charged. Yani electrons on the negative side goes to right, left plate makes their negative, and when this, because left plate is connected to positive, this becomes positive. But at the beginning, it was completely neutral. When a capacitor is initially connected, as soon as capacitor is connected to a battery, it draws the most current because it is empty and neutral. So it must be charged, which is called full. At the beginning, empty, like a hungry person. So a hungry person can start eating very fast, right? So it's like eating very fast, taking its charges. You have an electric current maximum at the beginning. But when you eat, and then finally you will slow down. So finally you will stop eating. It's similar like this. So at the beginning, capacitor, because it is neutral, it draws the most current at the beginning. When it was like it's not positive and negative. So both plates are neutral, 0 and 0. It draws the most current, maximum current. But at the beginning, when maximum current is maximum, but potential difference between the plates are 0 because no charge. Neutral, potential difference is 0. At the beginning, voltmeter reads. Then when it's charged, it becomes charged. This time, potential difference increases between the plates. Increases. Voltmeter reading is increasing, but electric current, because as you ate food and then you are going to slow down. So electric current is decreasing. Finally, when this capacitor is completely full, potential difference becomes maximum, but no more space for any more food. Capacitor's electric current becomes, again they are changing inversely, again out of phase. Yani, when a capacitor, electric current and potential difference are out of phase. But this time, which one is leading? Which one is maximum at the beginning? Electric current was maximum. This time electric current is leading. Now, what is the phase angle difference? The same as the pure coil. In pure coil in capacitor, phase angle difference is 90 degrees. Pi over 2 radian. Now, potential difference is lags behind. Electric current is leading. So, in a capacitor, potential difference equals capacitor lags behind the electric current I see by a phase angle of pi over 2. That's why we are going to write in here negative in equation of the potential difference. But in pure coil it was positive. In resistor, 0. We didn't write anything. Okay. Then phasor. Again, I'm making of phasor. Again, potential difference. VC and IC will not be in the same direction. There's a phase angle difference. They will be perpendicular to one another. But this time, potential difference will be lagging behind by pi over 2. We represent by negative pi over 2 in the phasor. And this is the equation for potential difference across the capacitor. And if there is an electric current is measured, if an electric potential difference is measured on a device, you can absolutely calculate opposition for that device. Yes, capacitor also has opposition to electric current, which can be calculated by VE divided by IE or VM divided by IM, just the way we calculate resistance and inductive impedance. So again, volt divided by ampere. The volt divided by ampere, what did we say? The opposition of the capacitor to electric current, this change in electric current is also ohm in units. What is this opposition called? Capacitive impedance, and represented by X sub C. Depends on what? First, it depends on the capacitance. Like a child, a monster, so they cannot eat equal amount of food. So monsters will eat more and more and more. So it's why as C increases, capacitance of the capacitor increases, opposition will decrease. They're inversely proportional. That's why inductive impedance XC is inversely proportional to the capacitance of the capacitor, how huge its capacity is. And also inversely proportional to frequency. Why inversely proportional? Because when capacitor is completely charged, it cannot take any more charge. How can a capacitor can be completely charged if it is DC? But in AC, how quick the AC is changing, capacitor can never get a chance to completely charge. Positive part of the AC makes charge, and a little negative discharge takes it back. And like this, eating and vomiting, it's maybe a little making, but it's okay, you can understand. Eating, vomiting, and positive, negative. So you can never have a completely full stomach. Huh? Similarly, when frequency increases, capacitor can never have a chance to be charged. That's why XC, opposition, decreases to electric current. And equation for XC is going to be in this case 1 over 2 pi FC. 2 pi f again omega, we can write XC in terms of again omega, 1 over omega C. And again frequency affects XC as you see. Then R, XL and XC. Frequency has effect or not? Let's get it. In R, no. In XL, yes. In XC, yes. So, increase or decrease? If frequency increases, so R, no effect. XL, but XC, yes. With this, we finished first part of 6.3. We will continue next lesson. RLC series and parallel and oscillating circuits.